This is CSaP's Science and Policy Podcast from the University of Cambridge, where we're bringing you the latest evidence and expertise to improve public policymaking. Hello, I'm Rob Doubleday. It's a pleasure to welcome you to this week's episode. This week on CSaP's Science and Policy Podcast, we're exploring the science of energy transitions. For today's episode, our main guest is Professor Sir Richard Friend, Director of the Winton Programme for the Physics of Sustainability at the University of Cambridge. We're also joined by two early career researchers, Winton scholar Jesse Allardice and the Department of Engineering's Karla Cervantes Barron. And what we're interested in talking about today is really the role of science in contributing to the energy transition that will be needed to meet net zero goals. So I'm interested, Richard, to start perhaps with what role science can play. What role can science contribute when thinking about these challenges?
Well, there is going to be a huge re-engineering of energy. It's being driven by all sorts of reasons. The ones that are particularly exciting at the moment are actually economic. We have discovered, somewhat to our surprise, that when we scale up and engineer correctly, solar, offshore wind have dropped in price quite remarkably. But behind that, these are areas which haven't really had much scientific attention. The science that gets pushed into an area is actually tied to what impact it might make on society, very often economic. And in many ways, an area such as solar cell technology has been a bit of an intellectual backwater for a long time because, in a sense, no one really cared. It has sort of survived with scraps cast over from regular semiconductor technology. What is so interesting is that when one looks at how well it works, it's very obvious that we could do much better.
Maybe you could talk a little bit about how to understand what's possible. How does a physicist approach the question of where to focus resources and attention?
So one of the questions we've been debating, primarily in the physics department, is when we look at any part of the energy infrastructure from generation to storage to use, is it running as well as it could be? Has it had its sort of full effort to make it as efficient as is possible, as set usually by the laws of thermodynamics, or is it sort of good enough and we've got along with it? And when one looks at that, it's very interesting to see how varied the answer to that question is across different sectors of the energy infrastructure. When I can pick some surprising examples, let me be positive to start with. Silicon, we think as having made remarkable advances, and maybe when we read about the end of Moore's law, we think that it's come to the end of the road. It's probably a factor of 100,000 times less energy efficient than it might be. It's quite remarkable. The physics is actually quite simple. Transistors, CMOS transistors, need 1 volt to switch. 1 volt is about 1,000 times larger than the voltages that are used in biological systems and biological brains, and energy associated with voltage goes as voltage squared. We know that there are other ways of fixing computation which would reduce the energy consumption. We don't know how it can be done yet, but we know thermodynamics, physics tells us that it could be done. So silicon is actually, it may be what we call silicon, it may get replaced with something else one day, but that sense that there are performance enhancements measured in orders of magnitude, not percent, that keeps that field so vital. You can go to other areas where there's been a huge amount of industrialization and efficiencies are pretty much as good as they can be. If you want to produce motion with a heat engine, if it's an internal combustion engine or a gas turbine system, actually the thermodynamics is working quite well. There's not a lot more we can do. But then in the middle, there are all sorts of areas where one might have to be careful how one defines efficiency. But there are quite big wins. Let me take the example of solar energy, which we know has become vastly cheaper in the last 10 years by a factor of 10, largely through successful industrialization in China. That's based on silicon. It's a single junction solar cell. very good solar cells convert something like 20% of the instant energy in sunlight into useful electricity. The other 80% is up for grabs, maybe not all of it, but there are ways that we know we can get it. The most attractive route is to stack another solar cell that absorbs higher energy photons and filters those out first before feeding the infrared photons down to the silicon below, making a tandem solar cell. And some very exciting advances where the UK has played a very strong role with perovskite semiconductors, for example, which show real promise. And there's a real prospect that we can lift the efficiency of solar cells from 20% to 30%. These are relatively conservative numbers.
I mean, this is a very, interesting case to look at. I want to turn for a moment to Jesse Allardice, who recently finished his doctoral work as a scholar in the Winton Programme for the Physics of Sustainability. Jesse, your group's been working on the next generation of solar panel technology. Can you talk about some of the research going on at the moment?
I'm a recent graduate of the University of Cambridge. I was doing a PhD there in the physics department, focusing on next-gen photovoltaics. So a large part of the projects that I was working on while during my PhD were focusing on next-generation technologies for photovoltaics. Basically, trying to find ways to get more sunlight out of the spectrum that comes in the incidences with our planet and get more out of that per photon there. We spend a lot of time looking at novel materials such as quantum dots, trying to come up with new fancy ways that either convert one photon into two or two photons into one high energy photon. The field itself as a research field is constantly evolving. Even if we just look at what the most common technology has been, say, for the last 50 years, the silicon-based photovoltaics, they've been slowly engineered to be more efficient, coming up on what one could consider like a threshold or a maximum of what efficiency you can get out of a silicon-based device, which is around 30%. Now, since even the initial discovery of the silicon photovoltaic, from very early on, there's been proposals of how to improve that. One of these was developed by Dexter in the 70s. He proposed that you could actually use a process called singlet exciton fission in a material such as an organic semiconductor. And you could place this on top of a silicon solar cell and get an extra boost in efficiency. This effectively would happen because the singlet fission material that would sit on top of the photovoltaic, when it absorbs a photon, actually produces two excited states in the material instead of one. That would be the convention that you'd see. And the idea was then you'd transfer these two electrons into this normal photovoltaic and you get a boost in the number of electrons per photon. Now, that's been proposed for a very long time, and it's actually only recently that there's been some really exciting progression in that work. So the team from MIT developed actually like a working demonstration of what Dexter was proposing, where they put a singlet fission material on top of a silicon photovoltaic and actually showed in principle it works. My work in the optoelectronics group in the physics department was working on a very similar idea, but instead of trying to electrically transfer these excited states, we were actually looking at optically transferring that. We believe that this is going to be a more beneficial method for taking advantage of this process, and hopefully will lead to improved watts per dollar for future devices and technologies.
Thank you, Jesse. Turning back to you, Richard, would you be able to build on that by telling us a bit more about how solar technologies work and sharing an update on some other innovations going on in this sector? So you talked about having, did you call them twin? So it could move from a single.
Yes, I mean in the trade that's called a tandem solar cell. So the problem with light, white light, is that it comes in all colours. Each colour, the sort of quantum of energy, the amount of energy in the photon, scales with the inverse wavelength. So red photons have more energy than infrared, but less energy than blue photons. The voltage you can get out of a solar cell is set by the energy of the photon that is absorbed, but it's set by the lowest energy that the semiconductor or the solar cell absorbs. So silicon does a very good job at absorbing the whole of the visible spectrum right down into the infrared, but it treats all the photons as having the same color. It's like a Model T Ford. They're just the same color. It's an infrared color, so the voltage is low. You can't get more than about 0.8 of a volt out of a silicon solar cell, even though most of the photons in principle could get you to 1.5 volts. So we should carry on using silicon to absorb the infrared, which it does very well. But if we put something on top of it, which is a visible absorber or further into the visible, then the photons that are absorbed from that top layer into that top layer can run a solar cell with a higher voltage. So for the same flux of photons, we get more energy because we've got more voltage. So this concept is pretty well worked out. There are very expensive exemplifications of stacked solar cells using 3-5 semiconductors that you would, say, put into a space satellite, but they're implausibly expensive for large-scale deployment. The current excitement is that some remarkably crude and dirty materials, generally called lead halide perovskites, behave as very, very clean semiconductors, and it's possible to make very cheaply lead halide perovskite solar cells that have really good efficiency, and you can color tune to provide the right complement to silicon. That's been done very successfully, actually, in Oxford, and that has come from nowhere. That has come out of the realm of pure research. It wasn't on the landscape even 5 years ago.
So that's potentially, from what you're saying, that's potentially, if what has so far been discovered can be scaled up, that could make, you're saying, a difference to the cost, the actual real cost of installing solar cells, and that will transform what proportion solar electricity generation can contribute to the energy mix. Is that what you're saying?
Absolutely. I mean, the UK is a little bit too close to the North Pole for solar to be wonderful, principally because we get a huge variation in the amount of solar energy received between winter and summer. It's about a factor of 6 difference between January and July. I think that's the right number. So it's been very hard to have solar that provided all the year-round electricity for the UK. Nevertheless, it's pretty attractive as part of the mix. If you head closer to the equator, and particularly to parts of the world where there are fewer clouds and less rain, it's just enormously attractive. It's attractive in Texas, it's attractive in California, in southern Spain, in quite a lot of the Middle East, in India. It's all seen as a key component of the new electricity generation.
So, I mean, from what we've discussed in the series so far, it's very clear that whatever path is taken to meet the climate targets of net zero within the next few decades, there'll be a much greater demand for electricity. So generation of electricity will just have to increase. So from your view of the kind of the physics, what proportion can we expect solar to play in a future mix of electricity generation, or is that the wrong question?
Well, the question of how much a technology ends up occupying market share depends on all sorts of factors, and the principal one is economic. And the economics of solar cells now are that what we always thought of as the expensive bit, the silicon that was always going to be too expensive, it's no longer too expensive. It's all the mundane bits, the use of the land, the installation on the land, the sheet of glass that covers it, that are, if you like, the fixed cost. And anything you can do to get more electricity out of that fixed investment looks like just straight cost reduction or profit, or a combination of the two. So I think the role of science is that if we can get the efficiencies up, we drop the costs. And as we drop the costs, the attractiveness for massive deployment goes up. And with solar, with wind, it's a really interesting sort of tipping point that the costs have come down to more or less match fossil fuel generation. If we could get them another quantum lower, that would be a very different world we'd be in if renewable generation was significantly cheaper than fossil fuel generation. That really would change our sense of what is possible and what will happen.
Currently, there's a lot of talk about the United Kingdom playing a leadership role in the world's transition to a net zero economy. Obviously, eyes looking ahead to the hosting of COP26 in Glasgow and the role that the United Kingdom can play in helping making a success of that. And there's discussion of the fact that, of course, the United Kingdom, in terms of the energy it generates and energy it uses, is only a small fraction of the global picture. But the case is made that because of the scientific excellence and the track record of science and innovation in Britain, that perhaps the contribution that the UK could play is at least as much in the fields of science and innovation. So do you think that even though solar is not necessarily going to be as important in the UK as other parts of the world, that it makes sense for the UK to try and contribute to improving the efficiency and reducing the cost of solar?
I think we should. And I don't think it is ever possible to divide up areas of economic activity into those that we should and those that we should not do. And if you look at great success stories in the UK, like ARM, why would you have the premier chip design company based in the part of the world where there's almost no manufacturing of silicon integrated circuits? Well, one needs to be very careful not to generate presumptions about what is not possible. In the case of many of these new technologies, they're coming from places that you wouldn't expect. There's a huge amount of transfer of ideas, of know-how, of technologies. Nations that have got integrated, broad science and engineering that are adept at being able to pull opportunities from one field to another can set a lead. In the UK, we probably ought to try rather harder to commercialize rather than hand over ideas. But there's tremendous value, obviously, to the overall global energy transition, but locally, we play quite a large role in many of the components, many of the high added value pieces of technologies that we often think of as being wholly owned by Asia these days.
Is there an example in respect to solar?
Well, in respect of solar, the final assembler is probably not the company that makes much of the profit. I mean, I do know that the glass that you put on top of a solar cell is just not a piece of bog standard glass. It's been engineered to be a rather sophisticated thing that does not reflect away light that should pass through it. There are some interesting things that are done to glass that add value, cause a solar panel that has got the right sort of glass on it to be more efficient than one that had the wrong sort of glass. And the Western glass companies are pretty smart, and they can make a profit in that space.
I want to take a moment to step back and look at the bigger picture of energy transitions more broadly. For that, I'd like to turn to the Department of Engineering's Karla Cervantes Barron. Karla's just finishing her doctoral work on energy systems and uses. Karla, what can you tell us about your research and some of the questions being addressed about energy systems and transitions?
I work in a group that focuses on resource efficiency in general. So the type of work we do tries to look at big picture systems, essentially. The part I've done has had to do with specifically trying to understand energy transformations, but from a service perspective. And that means looking at what the user wants energy for, essentially. And I've been doing analysis on how those transformations affect outcomes.
Could you elaborate on that? What are some of the areas of energy use your work explores?
We first have what we call primary energy, so which is related to having extracted some source. So, for example, coal or renewables, extracting it from the source and bringing it a step closer. After that, we have final energy. So that's when those resources have been further transformed and can power certain devices. And for example, here we have electricity. Then from that, we can think that there's a further transformation into useful energy. So a good example there is to think of you have electricity powering your home. but then you need, say, a cooker, an electric cooker or something to make the food you want. And so finally, I suppose there are different uses that we can have for all this energy chain. And among them, you can find things like illumination, sustenance, thermal comfort, transport. So there are several things that we need to consider. I suppose that the energy transition is important in countries like the UK, where there's a need to decarbonize systems. But for other countries, there's a need to kind of increase the availability of energy. And so really understanding what the services required is very important. So I've done a study for Uganda, actually, where I did specific calculations for some services, and I included, for example, cooking, just to really understand how the efficiency of devices translates further into what people actually need. The very last study that I've done has had to do with linking how different parts of that transformation is included in different policies, to be able to really say whether we're focusing more on generation, or if we're focusing more on other parts of those transformations. And so to really, say which countries could use some help in focusing on things closer to the final use. We are seeing that places like the EU generally have a lot of policies on generation, and in the past decade they are focusing more and more on like things closer to the end of the chain, so closer to final energy or final uses. So that's really interesting to see, and that has more to do with buildings at the moment. And at the same time, I see that overall countries where they're still developing are focusing like mainly in generation.
What are some of the policy challenges which lie ahead?
I feel that it is really essential if, as a whole, we try to understand these transformations a lot more up to those services that I was mentioning, and making data available for that is essential, because otherwise we can't really understand all those little efficiency losses that are happening. I suppose at the same time, making policymakers aware of this is important, because then there can be better regulation on certain devices or the way certain chains are formed. And I suppose the other big question is how to make sure that the gains that will happen from the energy transition are brought to all the people that will require it. And so to have, learnings from how to decarbonize, say, the electricity system to places that are currently building it is really important.
Thank you, Karla. And turning back to Richard, so what would you think, if people listening to this are interested in kind of government policy and the relationship between science and government policy? I mean, do you feel that there are opportunities for government policy to align better with what's kind of scientifically possible and what the technological opportunities are? Or do you think that, we're seeing a kind of a system that apparently looks chaotic, but actually creates opportunities that are the kinds that you'd want to see?
Well, I think the easy thing to say, and it is absolutely true, is that it's all about skills. And one of the things we have to have in the UK is a sort of infrastructure of opportunity that will cause school kids, undergraduates, graduate students to feel they have the opportunity to explore ways of playing a role in the transition to zero carbon. I mean, it's something that they're all even more passionate about than we are. And we need to have quite a wide funnel. We need to be able to demonstrate how almost any endeavor in, systems engineering or new materials or new architectures for solar cells or new ideas for better batteries, all of that has got to feel as though it's available because if we can bring talent in, then we will generate skills, we will generate good employment, we'll generate new companies. We have to think about how we generate the new energy companies that, alongside the Shells and the BPs that have played their role in the past and may be successful in making a transition or may not. We have to feel we have the confidence to grow from the ground up, and that means that we need to present opportunity. So if we narrow it down and say, well, UK only plays in some places and not others, that is a sort of recipe for running things down, not for building things up. And I feel that very strongly. If to take some examples in the energy world, the big breakthroughs that have been transformational have not come from the energy world. The huge transformation in lighting from tungsten filament light bulbs to LED lights that has completely, well, it's rather destroyed the lighting industry, actually, because they're cheap and they don't break. But that came out of the semiconductor world. The lithium-ion battery that we now have in vehicles was generated by Sony to put into the Walkman. Solar cells did not come from energy utilities. Again, that came from the semiconductor world. These are all transfers of ideas, of science, of technology that have moved laterally. And that's going to carry on happening. It'll carry on happening because when we look at what we might be able to do to sort of handle energy better, the science tells us that there's so many areas where we could be much more efficient, but it'll require radical new approaches.
So my question is really on the kind of geopolitics of the new energy. So some arguments have been made that it's going to shift balance of power geopolitically if oil plays a diminishing role in the energy mix and let's say solar plays an increasing role. How do you see that from your perspective as a physicist?
Well, I think that may well happen, that the oil-rich nations will discover that they've got a stranded asset. I mean, I think, but by definition, we think that has to happen. Otherwise, we won't get to zero carbon in time. But what is wonderful is that it then means in many parts of the world, many economies, many nations will actually be energy rich. If we do have a large amount of renewables, one of the really interesting opportunities is that we can see the problem of intermittency, that there are times of surplus and times of too little, as something we can engineer around. And the opportunity to work out what we do with surplus electricity, how we turn it maybe first to hydrogen and then into chemicals and fuels, or how we might store it in batteries or what other form of storage we want to explore. It's just a wonderful wealth of opportunity. And I mean, to be parochial about it, the UK fortunately has the North Sea and there's a lot of wind there. I just think we should plan to have too much electricity and then be extraordinarily good at working out what to do with it. And there's so many opportunities for science, for engineering, clever economic, financial models. It's just opportunity.
I remember seeing sort of a decade ago ideas of huge farms of solar generation in deserts, and the idea that these might be then piped around the world, as it were. And I've not seen those images in kind of popular imagination in recent years. What has happened to that? And do you think the idea of concentrating the generation of electricity through in particular places is still a prospect to explore?
Well, the idea of generating renewable electricity somewhere where the sun shines and there aren't too many sandstorms, and then piping the electricity a long way is really interesting. It was pushed pretty hard about a decade ago, quite substantially within Germany, where Siemens have played a big role in developing more efficient, lower loss power transmission. And that hasn't gone away. That's happening. The Chinese have put in a huge amount of high voltage DC power transmission. And that, again, is an example of technology that sort of came from from nowhere nowhere that was really called the energy industry. The technology that is transformational is DC to DC voltage conversion using solid-state electronics, power electronics, where it's still expensive, but we know that the costs are coming down and the efficiency is going up. And it's actually a transition away from silicon to higher bandgap semiconductors, gallium nitride and silicon carbide. Higher bandgap semiconductors can work at higher voltages, and they work as a huge, vibrant research and early stage engineering activity. A lot of it in the UK on high voltage semiconductors, and that will transform the power network. When we electrify, we're going to have to re-engineer our grid, and there is a real opportunity to change the technology. Quite a lot of it will go back to DC. It's more efficient. The long range losses, I should have mentioned that, are remarkably low. I mean, it's a few percent per 1,000 kilometers power loss now, probably less than the energy it takes to pump gas in a gas pipeline.
What I hear you saying is that, in terms of the science and the technology, there are already so many kind of prospects that are being developed that. Yes. And in fact, as it happens, the United Kingdom is not kind of completely out of the game, that is actually playing in some of these. And so there's a temptation, I think, for governments to look for sort of entirely new, novel solutions and think that, what's present isn't really up to it. But you're saying that actually there's a huge potential that's just kind of imminent right at the moment.
I think there is. I think we have to make a big push, and I have to give huge credit to the UK government for its feed-in tariff regime that got offshore wind to be absolutely globally leading in the UK. If we can get far enough along to the point where we know that there's going to be a market for new forms of storage or uses of surplus electricity and hydrogen, whatever, we don't have to come up with a full plan of exactly what is going to be the market, that is to say the scientific market, the economic market, the engineering market. If it's allowed free rein with the right investment climate, with the right regulatory environment, we'll come up with wonderful solutions. And we really should plan for the UK to be a sort of prime place for that to happen. And what prompts it is that we can be ahead of the game in having a large amount of cheap electricity that we will need to use in these sorts of ways.
Great. Thank you all for joining me today, and thank you for listening. We'll be back next week with Martin Rees and Claire Gray talking about energy storage and as part of the energy transition. If you're interested in learning more about CSaP's work, why not check out our annual report, which we launched yesterday. You can find it by visiting www.csap.cam.ac.uk/annual-report. Thank you for listening. CSaP's Science and Policy Podcast is a production of the Centre for Science and Policy at the University of Cambridge. This series is produced in partnership with Cambridge Zero. This episode was hosted by me, Rob Doubleday, and was produced by Kate McNeil. You can learn more about CSaP's work by visiting us on Twitter at CSciPol or at our website www.csap.cam.ac.uk. If you have any feedback about this episode or questions you'd like us to address in a future week, please email inquiries@csap.cam.ac.uk. Thanks for listening.